How many of you think that time flies by very fast? Like yesterday it was the month of March and it's suddenly May right now? Oh sorry, it's the month of August right now. You see, time flies by very fast, and in today's session we're gonna learn how to slow it down. Well, first of all, greetings to everyone present here. I am Akik Deshmukh from SSPMDS School and Junior College, and today with me, you and I are going to explore 1. How to slow down time. 2. You know how everyone hates commuting from one place to the other? It is so time consuming nowadays, right? So what we are going to do is learn a shortcut to it. We are going to learn how to open portals. Yes, you heard me correct. We are going to learn how to open portals through space, and is it really possible to do so? And 3. We are going to learn what are black holes. Black holes are one of the most interesting phenomena, and we are going to learn about them. Before we understand all of this, we first need to understand what is information. Typically, the information we talk about is visible to the naked eye. For example, this information tells us that the apple is red, round and shiny. But physicists are more concerned about the quantum information. This refers to quantum properties of particles that make up that apple. For example, its position, velocity and spin. Every object in the universe is composed of particles with unique quantum properties. This idea is invoked most significantly in a vital law of physics, which states the total amount of quantum information in the universe must be conserved. Even if you destroy the object beyond recognition, its quantum information never is permanently deleted, and theoretically knowledge of that information would allow us to recreate the object from its particle components. Conservation of information isn't an arbitrary rule, but a mathematical necessity upon which much of modern science is built. And these foundations are shaken around a black hole. Black holes are theorized none other than the person you see in this photo right now. I know most of you know him, but for the some of you who don't, it is Albert Einstein. As an incredibly massive collection of mostly hydrogen atoms that collapse from enormous gas clouds under their own gravity. In their core, nuclear fusion crushes hydrogen atoms into helium, releasing tremendous amount of energy. This energy is in the form of radiation, which pushes against gravity, maintaining a delicate balance between the two forces. As long as there is fusion in the core, a star remains stable enough. But for the stars more massive than our own sun, the heat and pressure at the core allow them to fuse heavier elements until they reach iron. Unlike all the elements that went before, the fusion process that creates iron doesn't generate any energy. Iron builds up at the center of the star until it reaches a critical amount, and the balance between radiation and gravity is suddenly broken. The star collapses within a fraction of a second. The star implodes, moving at about the quarter of speed of light, feeding more mass into the core. It is at this very moment that all the heavier elements in the universe are created, as the star dies in a supernova explosion. This produces either a neutron star or, if it is massive enough, a black hole. What you'd really be seeing is the event horizon. Anything that crosses the event horizon needs to be traveling at the speed of light to escape. In other words, it's impossible. So, you'll only see a black sphere reflecting nothing. Saw right now was a supernova explosion, and yes, those are the circumstances needed to create a black hole. This is how a black hole functions. As you can see, the arrows are indicating mass, and all the mass is getting concentrated at a single point in space. That point is known as singularity. Singularity is known as the point of infinite density. Singularity is usually described as a single infinitely small point in space without surface area. But points can't rotate, so a rotating singularity is not a point, and hence a rotating singularity is a ringularity. As you can see from the above image, that our universe was created from a single point in space and has been expanding ever since. This is known as the Big Bang Theory. Let me tell you, the universe expands 400 kilometers every second, and that rate is accelerating. It's not even a constant. According to one of the laws in physics, energy cannot be created nor be destroyed. So the energy that created atoms can't be created, and you cannot fully destroy that energy. So you might ask, where did this energy come from? Well, there is one more supporting theory that, see, right now the universe is expanding, it's getting bigger in size. So if I reverse time, what would I get? I would get a universe that came from a single point. So when the universe stops expanding, it will contract and form a black hole again, right? And that is why black holes are very important. Remember, this is just a theory, it has not been proved, but a black hole singularity could be the energy which created our universe. Dr. Stephen Hawking found the Hawking information paradox in 1974. Dr. Stephen Hawking is considered the best scientist of our generation. He dedicated his whole life studying black holes. Scientists work on the boundary of the unknown, where every new piece of information forms a path into a void of uncertainty, and nothing is more uncertain and potentially enlightening than a paradox. Throughout history, paradoxes have threatened to undermine everything we know, and just as often they have reshaped our understanding of the world. Today, one of the most biggest paradoxes in the universe threatens to unravel the fields of general relativity and quantum mechanics. Yes, it is the black hole information paradox. To understand this, we need to understand what is information, which we have already done. Every object in the universe which has a greater energy will try and get to a lower energy state. This is a law which is applicable to black holes and to everything else in the universe. When an object enters the black hole, it seems as though it leaves our universe and its quantum information becomes irretrievably lost. However, this doesn't immediately break the laws of physics, but it might still exist within the black hole's mysterious void. Alternately, some theories suggest that information doesn't even make it inside the black hole at all. Seen from the outside is just if the apple's quantum information is encoded on the surface layer of the black hole, called the event horizon. As the black hole's mass increases, the surface of the event horizon increases as well. So, it's possible that black holes swallow an object and it grows larger to conserve its quantum information. But whether it is conserved inside the black hole or on its surface, the laws of physics remain intact until we take into account Hawking radiation discovered by Stephen Hawking in 1974. This phenomenon shows that black holes are gradually evaporating over incredibly long periods of time. Black holes lose mass as they shed particles away from the event horizon. Critically, it seems as though the evaporating particles are unrelated to the information the black hole encodes, suggesting that a black hole and all the quantum information it contains could be completely erased. Does the quantum information truly disappear? If not, where does it go? While evaporating process is incredibly small, the question it raises for physics are far more urgent. The destruction of information would force us to rewrite some of our most fundamental scientific paradigms. But fortunately in science, every paradox is an opportunity for new discoveries. Researchers are investigating broad-range possible solutions to the information paradox. Some theorize that information actually is encoded in the escaping radiation. in some or the other way we can't yet understand. Others suggest the paradox is a misunderstanding of how general relativity and quantum field theory interact. Respectively, these two theories describe the largest phenomenon and the smallest phenomenon, and they are notoriously difficult to combine. Some researchers argue that a solution to this and many other paradoxes will come naturally with the theory of everything. The theory of everything is a single equation which would explain everything in a universe. To slow down time and make portals, we first need to understand the crucial concept of space-time. Space is the x-axis or a straight line. The second dimension of space is perpendicular to the x-axis and it is known as the y-axis. But is it that you can only move in the x and y-axis? No, right? There is also one more dimension, which is the z-axis, which explains depth. But I told you in the beginning that space-time is four-dimensional. So what do you think the fourth dimension is? Well, if you guessed it, you're correct. It is time. Time has its independent dimension. The concept you all have been waiting for. As you can see in front of you, the star and the planets are curving space-time. Remember, the stars and the planets are curving both space and time. As you can see, the star is more massive and hence it is curving space-time more. In the universe, matter bends space and space tells matter how to move. As the star is more massive, it is curving space and time more. So time around that star will work slower than the planets. Why, you ask? Well, it is because of time dilation. It states that time around heavier objects moves slow. There are more ways you can slow down time. Like, if you move with faster speed, time will move slow for you. And if you move at slower speed, time will move faster for you. Everyone is fascinated by wormholes. Kids, teens, adults. As kids, we see anywhere door, and as teens and adults, we see it in movies like Interstellar. But the idea is basically the same. Traveling the universe with a blink of an eye. And is it really possible? Today's last topic is wormholes, and let's discuss them quickly. Wormholes to be theorized were Einstein-Rosen bridges. They describe every black hole as a sort of portal to an infinite parallel universe. Let's try to picture them in 2D again. Empty space-time is flat but curved by the objects on it. As that object, space-time gets more curved around it. Eventually, space-time becomes so warped that it has no choice but to collapse into a black hole. As a result, a one-way barrier is formed. The event horizon, which anything can enter but nothing can escape. And after crossing the event horizon, everything gets trapped in the singularity. But maybe there is no singularity here. One possibility is that the other side of the event horizon is a bit like a universe again, but mirrored upside down, where time runs backwards. In our universe, things fall into the black hole. In the parallel universe, things get out of the black hole, like a big bang. This is called a white hole. Unfortunately, Einstein-Rosen bridges can't actually be crossed. It takes an infinite amount of time to cross over to the opposite side, and they crimp shut in the middle. If you go into a black hole, you won't become stuff coming out of the white hole, but you'll surely become dead. So to travel cosmos in a blink of an eye, humans need another type of wormhole, which is a traversable wormhole. Thank you everyone for your time. I hope you all enjoyed this video.